Imagine you are designed an AXA slave, FIFO, or adder. How do you know it works correctly for thousands of different input combinations? Are you going to manually apply every signal and check every output? That's impossible. This is where SV Testbench comes in. A Testbench automatically generates inputs, drives them to the design, observes the outputs, and checks whether the design behave correctly. Today, we will understand each component of SV verification environment from scratch and see how they work together to verify a DUT. Here, the test bench architecture starts with DUT. DUT means design under test, which is the RTL design that we want to verify. It could be an adder, FIFO, or AXA slave, AXA master, or any digital design. The DUT receives inputs and generates the outputs according to its functionality. However, the DUT cannot test itself. We need an external environment that applies stimulus and checks the responses. Here, to connect the verification environment with the DUT, we use an interface. An interface acts like a bundle of wires that contains all DUT signals in one place. Instead of passing dozens of signals individually between components, the AXI interface groups them together and provides a clean connection between the DUT and the test bench. Here, the important concept is the transaction. Here, a transaction is an object that represents a complete operation. For example, in an AXA write operation, a transaction write may contain write address, write ID, write address data, and other related information. Instead of sending individual signals, we everywhere verification components exchange transaction objects. Here, this makes the test bench more abstract, reusable, and easier to maintain. Here, the generator is responsible for creating transactions. It generates different test scenarios by randomizing transaction fields and sends them to the driver. The generator works at a high level and does not know anything about DUT signals. Its only responsibility is to create meaningful stimulus for verification. Here, the generator transaction is received by the driver. The driver converts transaction level information into the actual signal level activity on the interface. For example, if the transaction contains address and data, the driver drives those values into the DUT pins according to the required protocol timing. In simple terms, the generator thinks in terms of transactions, while the driver thinks in terms of signals and clock cycles. Once the DUT receives the driven signals, it processes them and produces outputs. Here, these outputs are absorbed by the monitor. The monitor is a passive component, meaningful, it never drives signals, it only watches interface activity, captures the inputs and outputs, and reconstructs them into transaction objects. The monitor essentially converts signal level activity back into transaction level information. Here, the transactions captured by the monitor and sent to the scoreboard. The scoreboard acts as the brain of the verification environments. It predicts what the DUT output should be and compares that expect result with the actual result observed by the monitor. It both match the test passes, otherwise an error is reported. The automatic checking eliminates the need for manually inspecting waveforms for every test. Here, the generator, driver, and monitor are usually grouped together inside an agent. An agent represents a complete verification unit for a particular interface. In large designs, the multiple interfaces, multiple agents may exist, each handling its own protocol. Here, about the agent environment, the environment is a container that creates and connects all major verification components such as agents and scoreboards. It ensures that the information flows correctly between components and manages the overall verification structure. Here, finally, at the top level is the test. Test creates the environment, configure it, and starts the simulation. Different tests can be written to verify different scenarios without changing underlying environment. Here, so the complete verification flow is very simple. Generator, driver, interface, DUT, monitor, scoreboard. Here the generator creates transactions, the driver applies them to the DUT, the monitor observes the DUT behavior, and the scoreboard checks whether the DUT response is correct or not. Once you understand this flow, learning advanced methodologies like UVM becomes much easier because UVM is built on exactly the same concepts, such as just in a more standardized and reusable framework.